Welcome to Spelling Bee Ninja. We are thrilled to have you join us on this journey of discovery and learning. Our mission is to empower young minds with knowledge and skills that last a lifetime. If you're eager for free educational content that engages the mind and stimulates curiosity, make sure to subscribe to our podcast. Let's dive into the fascinating world of mathematics, where proof and logic illuminate the path to understanding. Today, we are exploring the intriguing topic of mathematical proofs, the backbone of mathematics that provides certainty about various ideas and concepts. So, what exactly is a mathematical proof? Simply put, a mathematical proof is a logical argument that establishes the truth of a statement, leaving no room for doubt. This is distinctly different from scientific experiments that rely on evidence. Proofs ensure absolute certainty. Mathematicians build proofs using axioms, accepted truths, along with definitions and previously proven theorems, creating a chain of logical reasoning that leads to conclusions. The formal proof system we utilize today was largely developed by the ancient Greeks, with Euclid being one of the most prominent figures. Written around 300 BCE, Euclid's Elements remains one of the most influential works in history and laid the groundwork for a systematic approach to mathematical proof we still use. Next, let's discuss direct proofs, which are among the simplest and most straightforward forms. A direct proof begins with known facts or assumptions and logically proceeds to reach the conclusion. For example, to demonstrate that the sum of two even numbers is even, we start by defining two even numbers. Let's call them 2a and 2b. Adding these together gives us 2a plus 2b, which can be rewritten as 2a plus b. This shows that the result is also an even number, illustrating the clarity and elegance inherent in direct proofs. Did you know that direct proofs are the most commonly used in mathematics due to their straightforward nature? Now, let's talk about indirect proofs, or proofs by contradiction. This method operates on the premise that, in order to prove a statement, we first assume the opposite is true and explore this assumption. When this assumption leads us to a contradiction or an impossible outcome, we can confidently declare that the original statement must be true. A classic example is the proof that the square root of 2 is irrational. By assuming it is rational, we find that both numerator and denominator must exhibit properties that contradict the definition of being in simplest form. This famous proof by contradiction has roots in ancient Greece and is highly regarded for its cleverness. Another important method is proof by induction, particularly useful for proving assertions that hold for all positive integers. This proof comprises two essential steps, the base case and the inductive step. First, we demonstrate that the statement holds for the first integer, typically 1, and then we show that if it is valid for an integer k, it must also be true for k plus 1. This process establishes a chain reaction, confirming the statement is true for all integers. For instance, to prove that the sum of the first n numbers equals n times n plus 1 over 2, we start with n equals 1, verify its truth, then proceed to show that if true for k, it accordingly holds for k plus 1. Hence, proof by induction gets its nickname, the domino effect, where knocking down one domino causes all subsequent ones to fall. Let's take a moment to look at some terminology used in proofs. In mathematics, a theorem is a statement that has been proven to be true. A lemma, on the other hand, serves as a smaller, supportive theorem that aids in establishing a larger theorem. Lastly, a corollary is a statement derived directly from a theorem. You can visualize this as a building. The theorem is the main structure, the lemmas are the supporting beams, and the corollaries are the runes that follow from the overall design. This hierarchical structure helps organize mathematical knowledge coherently. Now, what exactly is a counterexample? It's an example that disproves a statement or proposition. In mathematics, just one counterexample is sufficient to show that a statement is false. For example, consider the claim that all prime numbers are odd. This is disproven with the number 2, which is a prime but also even. Counterexamples are potent tools in mathematics. They can refute broad claims without needing complex arguments. Searching for counterexamples helps refine ideas and averts the pitfalls of false assumptions. A relevant fact is that the conjecture positing that every even number greater than 2 can be expressed as the sum of two primes, known as Goldbach's conjecture, remains unproven, yet many counterexamples have been ruled out through extensive computer searches. Logical reasoning plays a critical role within the realm of mathematics. Essentially, logical reasoning is the method of using a structured approach to arrive at conclusions based on clearly defined premises or facts. It encompasses both deductive reasoning, where we apply general principles to derive specific conclusions, and inductive reasoning, which operates in the opposite direction, forming general conclusions grounded in specific observations. Deductive reasoning lays the foundation for mathematical proofs, while inductive reasoning is instrumental in generating hypotheses. Notably, deductive reasoning is what distinguishes mathematics from other academic pursuits, as it offers a level of certainty rarely found in other fields of knowledge. Similarly, there is a significant difference between deductive and inductive reasoning. Deductive reasoning starts with overarching principles and applies them to individual cases, guaranteeing that if the premises are true, then the conclusion must also be true. An example of this is the classic syllogism, all humans are mortal. Socrates is human. Therefore, Socrates is mortal. Conversely, inductive reasoning draws general inferences from specific instances. An example might be that I have only seen white swans, leading to the conclusion that all swans must be white. However, this conclusion is only probable, the next swan could very well be black. In mathematics, we primarily use deductive reasoning for formal proofs, whereas inductive reasoning is valuable for pattern discovery. Interestingly, the renowned Sir Isaac Newton utilized inductive reasoning to establish his laws of motion through careful observations of falling objects. Finally, let's address the application of mathematical proofs in real life. Mathematical proof is more than just an academic exercise, its implications weave through various fields. In computer science, proofs are crucial for ensuring software and algorithm correctness. Engineers depend on proofs to verify that structures like bridges and buildings will stand strong. In the realm of cryptography, proofs confirm the safety of security systems. Even in law, the logical reasoning parallels used in mathematical proof shape arguments and decisions. Medicine relies on logical reasoning to ascertain the effectiveness of treatments through structured clinical trials. In finance, rigorous proofs help validate mathematical models, ensuring their reliability. An interesting fact is that formal verification, which uses mathematical proofs to check software correctness, is increasingly crucial in high-stakes areas such as aviation and healthcare. To summarize, the essence of mathematical proof in mathematics cannot be overstated. Proofs provide the certainty we crave in a field where evidence alone is insufficient. It builds a solid foundation of knowledge that endures through time. Theorems, once proven, become eternal truths. Moreover, the practice of engaging with proofs develops critical thinking, logical reasoning, and a rigorous mindset that are vital in any discipline. This quality is what sets mathematics apart as a universal language of truth. And did you know that the Pythagorean theorem, a cornerstone of mathematics, has over 400 different proofs, including one discovered by United States President James Garfield? Proof is both a rigorous and creative pursuit, and through understanding its principles, we can better appreciate the beauty that mathematics offers. To wrap up our session on mathematical proofs, we explored what a mathematical proof is: a logical argument that establishes the truth of a statement with complete certainty. We learned about direct proofs and how they clearly demonstrate truths through logical steps. Indirect proofs helped us see how assuming something false can lead us to establish a truth, while proof by induction illustrated the chain of reasoning essential for proving statements for all positive integers. Additionally, we discussed fundamental terms like theorem, lemma, and corollary and understood the crucial role that counterexamples play in testing the validity of statements. Finally, we examined how logical reasoning underpins all of mathematics and discovered the real-world applications of these proofs. Mathematics is not just numbers and equations, it's a language, a framework of truth that shapes the very fabric of our world. Thank you for joining us today on this enlightening journey through the world of mathematical proofs. We hope you found it informative and inspiring. If you enjoyed this episode, don't forget to subscribe and share it with friends who are equally passionate about learning. Your support helps us continue to bring you engaging content that empowers learners everywhere. Until next time, keep questioning, keep exploring, and let the beauty of mathematics inspire you every day. Stay curious.